understand electric circuits, and that is the electric charge. Electric charge can be positive, negative, or neutral. The positive and negative charges attract each other, whereas like charges repel each other. So what makes a particle, like the ones I have shown here, charged? It has to do with the quantity of protons and electrons on a given particle. If you have more protons than electrons, you end up with a positive charge. If you have more electrons than protons, you end up with a negative charge. And if you have an equal amount, your net charge is 0. So a little bit more about charge. It is a conserved quality. Which means what? Well, it means that you cannot create or destroy charge. It's something that just exists. It can be moved, but it cannot be created or destroyed. There are other types of conserved things, and that would include mass, energy, and momentum. And for anybody who fondly looks back at kinematics, you'll recognize that as momentum. So charge is also quantized, which means that you can only break it down so far. It has a minimum value that it can be. And the charge on one electron is that value, and it is 1.61 times 10 to the negative 19th coulombs, which is also the charge on a proton, except that's positive. So any value of charge, positive or negative, has to be some multiple of these numbers. Whether it's a million of them or whether it's just one of them, you cannot have half of this charge. So one of the most direct uses of charge comes in the form of Coulomb's law, which states the force between two charges is equal to a constant times the quantity of the first charge times the magnitude of the second charge, all over the radius, or the distance between them squared. Q is charge. R is the distance between charges. K is Coulomb's constant, which is 8.99 times 10 to the 9th Newton meters squared per Coulomb squared. And the units matter, and I'll show you why in a bit. Force here is in units of newtons. Charge is in units of coulombs. And our distance is in units of meters. So let's work a quick example problem. If we are given charge 1 to be -1 microcoulombs, and remember micro is 10 to the negative 6th. Q2 is -2 microcoulombs, and the distance between the two is 1 micrometer. What is the force between these two charges? So let's draw it out. We've got Q1, we've got Q2, we have this distance, which we know to be 1 micrometer. Now let's figure out the force between these two. Force is going to equal Coulomb's constant, Newton meters squared over Coulomb squared, times charge 1 which is -1 times 10 to the negative 6 coulombs. Second charge is -2 times 10 to the negative 6 coulombs, divided by the distance between them, 1 times 10 to the negative 6th meters squared. Now if you put this all into a calculator, you're going to get a value out, and that value is this, or 17.98 times 10 to the 9th newtons. So just for a point of reference, to break a human femur, it takes 4,000 newtons. So this would be a little bit overkill if you were trying to apply charges to break femurs for some reason. Don't do that. It's probably not ethical. So why do the units matter in this constant? Well, let's look at how our units worked out as we calculated our values. We had Newton meters squared over Coulomb squared. I'm just going to use units right now. Multiplied by some value of coulombs times some value of coulombs over meters squared. That gives us Newton meters squared over Coulomb squared times coulombs squared over meters squared. The coulombs cancel out, meters squared cancel out, and we're left with newtons. So you will see me do unit analysis on practically everything. It's a good way to know whether or not you screwed something up. As I was working on this earlier, I had a number that was just 10 to the 3rd instead of 10 to the 9th, and I realized it's because I had not squared my distance, and I knew that because my units didn't work out. So that is the basic charge. So to recap, positive, negative, neutral. It is conserved at all times, can just be moved, not created or destroyed. It's quantized in that the smallest value of charge you can have is 1.61 times 10 to the negative 19th. Everything else is a multiple of that. And then our example problem with 2 charges. Also, what direction is the force that these charges experience? Well, they're the same sign, they're both negative. So Q2 is going to experience F to the right, and Q1 is going to experience F to the left. And that's all for now.